How do you propose a reaction mechanism? I will be giving 3 examples on how to propose a reaction mechanism. So any reaction mechanism is acceptable as long as it follows the properties of a reaction mechanism. So during our lecture, I highlighted 2 important things about a reaction mechanism. Number 1, if you add all the elementary steps, you should get the overall reaction. And number 2, the derived rate law from your proposed reaction mechanism must be the same as the experimental rate law. So let's answer this first example. You have a reaction here and you are given the experimental rate law. So propose a 2-step mechanism for this reaction consisting of a fast reversible step followed by a slow step. So again, you can be as creative as you can be with your elementary steps. But now here in this example, we have several hints. So the first hint that we have is that the mechanism must be a 2-step mechanism. So limit your mechanism into 2 steps. And you have a fast reversible step, which is your first step. Your second step is a slow step. Okay, so let's imagine. Let's say your first step is NO plus Cl2. So it should be reversible. So we use the double-headed arrow, forming NOCl plus Cl. And then this will be followed by NO plus Cl. So this is a slow step. It's not indicated that it's reversible, so we will just use a single-headed arrow and you form NOCl. So again, what do we check? If we add the elementary steps, we should get the overall reaction. And for this proposed reaction mechanism, we indeed get the overall reaction. So our next step is to derive the rate law from this mechanism. So what do we do? Again, since we are sure that this is an equilibrium reaction, because the problem indicated that it's a reversible step, then we can use the equilibrium method. And we know that our basis will be the second step because it is the slow step. Now, the problem with the second step is that you have an intermediate appearing in it. So your intermediate is the monoatomic chlorine. So it's in the rate law for the slow step. So we need to find a way to eliminate this, and that's where the equilibrium method comes in. So according to our equilibrium method, so first we write the rate laws for the forward reaction of the first elementary step. And then we also write the the rate law for the backward reaction of the first elementary step. So that's NOCl times Cl. So applying the equilibrium method, so the equilibrium method tells us that the rate of the forward reaction is equal to the rate of the backward reaction. So we just equate rate 1 and rate -1. So we have K1 times NO times Cl2 equals K-1 times NOCl times Cl. And we isolate Cl and we get K1 times NO times Cl2 over K-1 times NOCl. So this expression, we substitute this for Cl here in the rate law for the second step. So now we have rate sub 2 equals K2 times NO times this whole expression for Cl, concentration. So that's K1 times NO times Cl2 all over K-1 times NOCl. So if we let K be K2 times K1 over K-1, then we have the overall rate as K times NO squared times Cl2 over NOCl. And here, with our proposed mechanism, we see that it's not acceptable because the derived rate law is different from the experimental rate law. So this is not a plausible mechanism. Okay, so let's try to think of something else. What if, so here in our proposed mechanism, it's one molecule of NO and a molecule of Cl2 colliding. What if we have as our first step the two molecules of NO colliding? And then they will form, so this is the first step is reversible. They will form N2O4, so they will just combine. And then the second step will be your intermediate N2O4 colliding with Cl2, forming two molecules of NOCl. So adding the two steps will give us the overall reaction. So in this aspect, our reaction mechanism is acceptable. But again, we have to check if the derived rate law is in accordance with the experimental rate law. So again, our basis will be the second step. So in the second step, we have the intermediate N2O4 times Cl2. So again, this is our problem. We have to eliminate N2O4. And again, we do that by the equilibrium method because we know that the first step establishes equilibrium. So the rate of the forward is equal to K1 times NO squared. And then the rate of the backward for step 1 is equal to K-1 times N2O4. So again, applying the equilibrium method, rate 1 or rate of the forward reaction is equal to the rate of the backward reaction. So we have K1 times NO squared equals K sub -1 times N2O4. And then isolate the concentration for N2O4. You get K1 NO squared over K-1. And we substitute this for N2O4 here. So we have rate equals K2 times K1 over K-1 times NO squared times Cl2. And again, let K be K1 times K2 over K-1. We now have the overall rate law. So rate equals K times NO squared times Cl2, which is the same as the experimental rate law. So this proposed mechanism is plausible. So again, there might be another mechanism that you can think of aside from this one, as long as you check if you add the elementary steps, you get the overall reaction, and the derived rate law from your proposed mechanism is the same as the given experimental rate law.